Hello everyone. In this video, we will discuss the important topic of energy models. So in computational material science, a key quantity that's of great importance is computing the energy for a system of atoms. And it turns out that there are several models to compute this quantity. Um, Here we will briefly discuss the key categories of these models. So we can classify them into five categories. The first one is the empirical uh, energy models. The second category, machine learning potentials. The third category here is physics-informed machine learning potentials. So physics informed machine learning potentials. And then the fourth category is semi-empirical methods or semi-empirical energy models. And finally, quantum mechanical. So the final is quantum mechanical. So we have five ways or five different models to compute the total energy for a system made of atoms and possibly also electrons. As we said, the energy is really the fundamental quantity in computational material science, and out of which we can compute several useful properties. So let's try briefly to describe each one of these five models. Empirical energy models. In empirical energy models, the electrons are not treated explicitly. Like you don't see electrons, only just atoms. So no explicit electrons. Instead, the effect of the electrons, for example, if they are leading to a covalent bond or if they are leading to van der Waals interaction, is taken via empirical equations. So no explicit electrons, instead electrons effect considered via empirical equations. We will discuss some of these equations, of course. The classic example is Lennard-Jones potential. This is one of the classic examples for empirical energy models, and we will discuss it in details in a subsequent video. One last comment about empirical energy models is that they are really physics-based. So there is a great amount of physics inside them. And sometimes some of the terms in the empirical energy models have been actually derived physically um, by physics arguments. Machine learning potentials are more modern, and let me comment on them is that um, they are basically mathematical models used to compute the energy via interpolation. So the energy of the system, so I have certain energy, certain states with known energies. These could be computed with maybe quantum mechanics. And then in machine learning, we have some mathematical function that's used to interpolate among these known states. So here, let's write here. So these are math models used to compute the energy using or via interpolation. Definitely, you can extrapolate as well, but this is usually very, very risky in machine learning potentials. They are good for what they are fitted for. One major problem here in machine learning potentials, some people might find this a little bit a biased opinion, is a lot of physics insight is lost because we are really using math functions rather than physics-based functions to calculate. So some physical insight is lost, unfortunately. Having said that, they are actually for what they are fitted for, they usually perform very well. There is also the so-called physics-informed machine learning potentials. So here we do have empirical energy models. They are physics-based, However, the parameters inside the model itself are fitted by machine learning during the simulation. So it's a mix between the previous two, between the empirical energy models and the machine learning potentials. So we do have physics-based models, but the parameter of the model are fitted by machine learning during the simulation. So let's write this comment here. So we have physics-based models whose parameters whose parameters are fitted on the fly by machine learning. So definitely here you are getting the best of the two worlds. The world of machine learning potentials that allows you to sample or to interpolate among a large space of data, and simultaneously you are still maintaining the physics insight that's coming from the empirical energy models. Semi now, so for in the first three categories here, electrons didn't appear. So there is no explicit treatment for electrons at all in the first three categories. Electrons will start to appear in the last two categories, in the semi-empirical and the quantum mechanicals. So in the semi-empirical models, electrons are treated in an approximate way. So here we start to see electrons. So electrons are treated in an approximate way. Um, in an approximate way. Some key empirical energy model or a method that's used to compute the energy that's considered semi-empirical is the famous tight binding model, widely studied in physics. Quantum mechanical, now in quantum mechanical, this where the electrons are considered using quantum mechanics. There are still, of course, approximations used in quantum mechanical methods, but the level of approximations is much, much less, let's say, in comparison to semi-empirical methods. So let's say here that electrons, of course, there are still atoms, but the key new ingredient here is electrons. So electrons treated using quantum mechanics, QM, and there is still level of approximations, but it's not as great as in the semi-empirical model. A key example or a key method of wide use in quantum mechanical techniques is the so-called density functional theory, uh, among other methods. For example, Hartree-Fock and other techniques used to calculate the total energy of a system using quantum mechanics. So let's summarize again. We have variety of models available to calculate the total energy, starting from the empirical energy models, where no explicit treatment of electrons, all the way to quantum mechanics, where electrons are treated explicitly. Still, there are some approximations, but not a huge amount of approximations. If we try to, draw some arrows here to indicate speed or accuracy, we would say that generally speaking, as we go to the right, the computational cost increases. So that's a general trend that as we go to the right, the computational cost increases. So definitely a quantum mechanical simulation would take much more time than the empirical energy models. Typically also, again, this is a typical thing. Don't expect it to be a general trend. You might end up with a violation of this typical behavior, that the accuracy increases as we go to the right. Again, you might actually have an empirical energy model that might sometimes do better even than quantum mechanics. A classic example for this is just water, liquid state water, and that's a little bit surprising. But that's actually One devastating example where empirical energy models can sometimes perform much better than quantum mechanical models in some properties. Again, not a general trend. While another arrow, the last arrow I will draw here is going to the left, where the number of atoms that we can simulate on a computer actually increases. So the number of atoms increases to the left. So definitely the ones that are computationally less expensive is where you can actually model a large number of atoms. We are talking here in empirical energy models on typical number of thousands of atoms, and one can go even to millions if you want. While in quantum mechanics, we are talking about hundreds, and you can go to thousands if you have the sufficient resources for such a calculation. Thank you so much, and talk to you in another video.